get started here. All right, so just a little bit of feedback. How was the first assignment, homework? So hard? Or was it okay? Just kidding around. Is that right? What's that? Okay, the YouTube videos, were they helpful? Very good. Okay, again, I tend for them to be helpful. Please don't just, as soon as you get stuck, jump to the video. Okay, don't. That's not a good way to learn. Okay, but it's there, so after you struggle through it, you can go back and check and see if you were on the right track, or oh, oops, you did not understand the concept correctly and stuff. So, oh, that's a good reminder for myself. I will silence my own phone. Okay, cool. All right, so I think we left off just talking about IQR, quartiles, things like that. We touched upon the mean and how to calculate the mean with that formula. Okay, so once again, so I'm going to finish off Chapter 4, and then we're going to blitz through Chapter 5. Chapter 5, I'm only going to talk about a few of the topics there, not the entire chapter, and then we'll get through as much of Chapter 6 as we can. It'll be my goal to finish Chapter 6, but we'll see what time allows. Okay, so this is Chapter 4, and we talked about the mean, and we said the mean is equal to the sum of y divided by n. N being the number of numbers that you have. Y is each number, and this symbol sigma means you add them up. So you sum them up, sum all the numbers up, and you divide by how many numbers you have. Okay? Now the interpretation or the meaning behind the mean is that if you have some distribution, okay, and imagine that we've got some histogram that looks like this. Okay? Imagine cutting this piece out, okay, cutting this thing out of wood or something, and then placing it on a seesaw. And we want to see where the balancing point would be, okay? And if the if it looks like the balancing point is, I would say about here, okay, this is where the mean is located, okay? So when you run through this formula and you get the actual calculation, this would actually, it would reveal the location of this balancing point, okay? That is slightly different from the median, okay? If you remember the definition of the median is the central point, okay? Central point, basically the spot at which you have half the numbers above and half the numbers below. Okay, so let me say half below. Okay, and we have a question.
Do you have to memorize the equation, or just memorize the concept behind the equation?
Just memorize the concept behind the equation, okay? But the equation, and right now this equation may not be any easier to memorize than the concept behind the equation, but sometimes in the future the equations will be, in fact, easier to memorize. Or not memorize, but it will help you remember the concepts behind the equation, okay? All right, so when we have symmetric distributions, okay, so symmetric being, so just pretend that instead of drawing histograms, so histograms are these bars, okay? Instead of drawing histograms, I'm just going to draw smooth lines, okay? So just imagine I've smoothed out all of these bars, okay? So if we have something like this, this is symmetric. For symmetric distribution, the mean would be at the center. This is the balancing point. And the median is also at the center, okay? And we would have half the points above and half the points below. So just remember that for symmetric, the mean is equal to the median. Okay? So let's talk about some skewed distributions. So if I smooth this out and I drew this out like this, okay, what kind of distribution do we have here? Skewed right. Okay, so this is something that's skewed right. And the median, again, is the the halfway point. Okay, we would have half the points above and half the points below. Okay, and I would argue that somewhere around here, this is going to be the median. All right. The mean, on the other hand, because we've got these points in the tail, all right, and again, this is like a seesaw, all right, and if you remember as a seesaw, if you were the lightweight kid and your friend was the heavyweight kid, okay, you would have to sit further back, and then the heavier kid would have to lean forward, right? If you guys remember this, or like if you're balancing against like your parents would have to come really close to the to that axis, that fulcrum point, and you would have to be far away, okay? And likewise here, in order for the balancing act to work, the median has to shift in order to compensate for these points out here. And so the median gets drawn out here, okay? Or, I'm sorry, not the median, the mean. The mean gets drawn out here. Okay? So this is a good point to know that for distributions that are skewed right, the mean, okay, is greater than the median, okay? So because it's drawn out this way, okay, as we go to the right, like on the number line, this number is bigger than this number. The mean is bigger than the median, greater than the median. And just the, I think I can actually fit this on the same graph here. Well, we'll just move it down here. Okay, and just the converse is also true. Okay, so this is something that's skewed left. For skewed left, okay, again, we've got the median somewhere around here, and then the balancing point, the mean. So this is the median, and this is the mean. The mean is less than the median. Okay, so for skewed left, the mean is less than the median. Okay, okay, and so that's just something to consider for here. And you got there's a homework problem that I've assigned this week. You've got to think about it. Okay, how many points are above, how many points are below what they call the average, and that will help you decide if something is skewed right or skewed left. Okay. Okay. And all right. And so we left off last week touching on the IQR. IQR being the interquartile range, or the location of the third quartile minus the location of the first quartile, and we get some number here. So this is the IQR. All right. And I didn't talk about the range itself, but the range is a very simple concept. And this is the largest point, or the maximum, minus the smallest point, or the minimum. Okay. And so these are measures of spread. Okay. Spread being how far apart the numbers are located, or how close they are compressed together. Okay. And so if they're all compressed together, the spread is small. The IQR is small, the range would be small. Okay? If the numbers are very far spread out, you'd have a large IQR and a large range. Okay? Both measures of spread would be large. Okay? And sometimes, because just the way some numbers appear, sometimes the range doesn't change too much, or the range will, you might have still a large range, but within all those points of numbers, you might have a whole bunch of points clumped together, giving you a small IQR, or you might have the points spread out. So for example, and again, I hope it's okay that I'm just drawing smooth lines rather than all these rectangles for histograms. Okay, but the underlying idea is the same. So I might have two distributions here. Okay, and here I've got something like this. All right. And then over here, I might have something like this. Okay, so in both cases, the range is about the same. The largest point minus the minimum point, okay, the smallest point, that distance is going to be the same for for both of these, okay? But over here, down here, most of the numbers are compressed or close to the center here, okay? And over here, you got kind of this wide spread. So I would say that the IQR is smaller for this one than this one. This one has a larger spread than this one does. So this one has the larger IQR, and this one has a smaller IQR, even though the ranges are the same, even though the max for both of these are the same, minus the min is the same for both of these. So I'll say these two. Okay, same range. Okay, but this one has more spread. So that means larger IQR. And this one has a smaller spread. And smaller IQR. Okay, so this is so the IQR and this is all pretty good. All right. Okay, and there's one more thing that we use to measure spread, and that is the standard deviation. Okay, so all three of these, all three are measures of spread. Okay, so just like the mean tells us where the center is, or kind of where that balancing point is, and the median also tells us where the center is. So the mean and the median are measures of center. The IQR range and standard deviation are measures of spread. We have a question.
So those three things are used to show how clump.
Correct. These three will describe how either dispersed the numbers are or how clumped together the numbers are. Okay? All right, so standard deviation. This is one of those terms that you hear thrown around, but you never actually know what it really means, okay? And I'm going to show you how to calculate the standard deviation, but I have a feeling that even after showing you how to calculate the standard deviation, it doesn't mean a whole lot to you, okay? And that's okay, all right? It's kind of like as a kid, you might have heard like what gas mileage was all about, but until you started driving, you never really cared about gas mileage, okay? So right now, I'm going to tell you what standard deviation is all about, and you're just going to be like, oh, that's nice. But you know, maybe by the end of today's lecture, you'll at least have a feel for what it's about. But here, I'm just going to go into the calculation of it, and maybe we can kind of start to understand what it's about. Okay, so the standard deviation. We're going to take numbers here, okay? So let's say we have the numbers 4, 3, 10, 12, 8, 9, and 3, okay? So if we were to, let me toss this up here, okay? If we were to rearrange these, we would have 3, 3, 4, 8, 9, 10, and 12, okay? All right, and I don't know. We could draw a histogram, and we could go from 0 to 5, or not 0 to 5. It would be 0 to 4, 5 to 9, 10 to 15, and I don't know, we would have 3 here, 2 here, and 2 here. Okay, 1, 2, 3, 4, 5, 6, 7. And our histogram, this is a very rudimentary histogram, would look like, this is actually at 2. All right, and you don't need to draw this, okay? But this is just to show, this is kind of what our numbers look like. And so this set doesn't mean a whole lot to us, but we're just going to calculate the standard deviation on this anyway. Again, the standard deviation is a measure of spread. And for a small set, it's hard to appreciate what the standard deviation means, but for larger sets, it gets more tedious to calculate, but it's not too bad. Okay, so the first step, so the step the first step in calculating the standard deviation is find the mean, okay? All right, and so in this case, we add up all of these numbers, 4 plus 3 plus 10 plus 12 plus 8 plus 9 plus 3, okay? We add all of those up, and what do we get? This is 7, 17, 29, 37, 46, 49, okay? So we have 49 divided by how many numbers we have. We've got 7 numbers. So our mean is equal to 7, okay? All right, so finding the mean, this is okay with everyone? We get 7, all right. All right, step 2. Subtract the mean from all numbers, okay? Okay, so I'm going to subtract 7 from each of these numbers, okay? So I'm going to do minus 7, okay? I'm going to apply that to all of these numbers. Actually, let me space these numbers out a little bit more so we can see what's happening here. Okay, so what were the numbers I got? 4, 3, 10, 12, 8, 9, and 3. Okay, so I'm going to subtract 7 from each of these numbers. So I get, so after applying minus 7 to all of these, so I get 4 minus 7 is negative 3, 3 minus 7 is negative 4, 10 minus 7 is 3, 12 minus 7 is 5, 8 minus 7 is 1, 9 minus 7 is 2, 3 minus 7 is negative 4. Okay, so this is step 2. Let me just write step 2. Okay, step 3 is we square the differences. Okay, so now that we have the difference here, so we take this minus 7 and we get all of these numbers. Now we're going to square every single one of these numbers. Okay, so this step 3, we square them. So minus 3 squared is 9. Okay, so it doesn't matter whether it's positive or negative. When you square something, everything ends up positive. Okay, so this squared becomes 9. Negative 4 squared becomes 16. 3 squared becomes 9. 5 squared becomes 25. 1 squared becomes 1. 2 squared becomes 4. And negative 4 squared becomes 16. Okay. So that's step 3. Step 4 doesn't stop. Okay, now we add up all these, add up the squares. Okay, so we do 9 plus 16 plus 9 plus 25 plus 1 plus 4 plus 16. Okay, so what does that end up being? So this is 25, 50, 75, 80. Okay, so when you add up all of these numbers, okay, they add up to 80. Okay, and you can plug them into a calculator and you'll still get 80 when you add them up. All right. Step 5 is divide 80 or divide up the sum. Okay, divide the sum by n minus 1, okay? All right, now I don't want to get into the explanation behind n minus 1, but these smart math people figured out that n minus 1 is better than dividing by n, okay? So what we've done so far, okay, is we're finding the kind of average squared distance from the mean, okay? And I'll write this up in a second here, and I'll try to explain it here, but anyway, at this point, I'm just going to say divide this sum, which is 80, by n minus 1, okay? So in this case, n is 7. We have 7 numbers, so 7 minus 1 is 6. So we're going to do 80 divided by 6. So step 5 is 80 divided by 6, And that turns out to be 13.33. Okay, 80 divided by 6 is 13.33. And the last step is take the square root. Okay, so step 6 is we take the square root of 13.33, and I get 3.65. Okay, so right now I just told you a bunch of steps that you have to do, and I'm hoping none of these steps are too extraordinarily complicated. It's just the process is kind of a lot to take in all at once. Yes, we have a question.
So is n the mean, or is n the number of numbers?
N is the number of numbers that you have. N is always going to be the number of numbers that you have.
Just a coincidence that the mean was 7?
Yeah, it was a coincidence that the mean was 7 and we happen to have 7 numbers. Yeah, that was a coincidence. Yes?
What's the difference if there was a capital N and a lowercase n?
Capital N is rarely used and applies more to populations, okay? So don't worry about that. Yes?
Is standard deviation always positive?
Standard deviations will always be positive, okay? Standard deviations will always be positive. That's a good question. All right, so all of these steps can be summarized with one formula, and this formula is a little bit scarier than our formula for the mean, but all the steps are included in it, and it's not too terrible, okay? I feel like, all right, so the standard deviation is given by the symbol sigma, okay? Sometimes it's given by the symbol s, okay? This is the standard deviation, okay? Don't worry about it too much, but this is for populations, okay? And S is for samples, all right? Okay, but they both standard deviations here, all right? So anyway, the formula. Okay, all right, so simple enough, right? Okay, let me, so once again, it's not too bad, all right? I'll just show you where each of these steps come into the formula. And it's kind of like when you write a formula, you start on the outside and you work in. Okay, so it looks like we're doing all the steps backwards, but I'll show you. So first, we find the mean. That's given by this y bar, okay? So so I'll leave this formula here and I'll write the duplicate formula here and I'll annotate it. Put all these notes on it. Okay, so the step 1 was finding the mean, okay? That's step 1, we found the mean, and that's y bar, okay? Step 2 is we subtract the mean from every number. That's this y minus y bar. Remember, when you see a formula and you see y, that means each number. So we're taking each number, y, and we're subtracting the mean from this. So that the minus sign is step 2. Okay. Step 3 is we square the difference. So once you figure out that number, we're squaring it. And that's where this squared 2 comes in. Okay. Step 4 is you add up all of these numbers. So once we found the mean, we subtracted the mean off of every number, and we squared it. Now we're going to add all of those up. Okay. And so this summation here, that's step 4. Okay. Step 5 is we divide everything by divide this entire sum by n minus 1. Okay, so this part down here, that's step 5. And then the last step was we take the square root. Okay, and that's given by this symbol here. Step 6. Okay, I don't know if that makes it any easier, okay? But you've got this crazy formula. But each step along, so when you see this crazy formula all by itself, it's a little overwhelming. But when you break it down into just steps, it's not too terrible, right? It's kind of tedious, all right? This was a bit of work for 7 numbers. You can imagine it being extremely tedious for like 30 numbers. And that's why we have computers, and the computers will crunch these numbers for us very quickly. We have a question.
Can you briefly explain how we use n-1?
All right, so n-1, it has to do with this concept called degrees of freedom. It's not, it's beyond the scope of the course why it's n-1 versus n, okay? It's just, overall, if you keep looking at it, n-1 is a better approximation than n by itself, okay? And don't sweat it. Just go with n-1 for now. Yes?
I know it's not relevant right now, but on the exam, are you going to give us like 30 numbers to?
No, I won't. Okay, I might give you 5. All right. Just because, what? I mean, find the standard deviation of 5 numbers. Okay, if you can do it for 5 numbers, you can do it for 30 numbers. Okay, except with 30 numbers, you're more likely to make a typo on your calculator and get the entire problem wrong. Okay, but with 5 numbers, I think that's a fair number of numbers. Okay, and you'll have a homework problem to exercise your newfound knowledge here, okay? And so let me just give you kind of a word definition of the standard deviation. So we've got this formula definition for the standard deviation. And in words, as close as I can make it to regular English language, this is a definition of the standard deviation. Okay? Standard deviation is the square root of the quote-unquote average, because it's not quite the average. If it was the average, we would divide by n, but it's the quote average because we're dividing by n-1. Average squared distance from the mean, okay? Okay, now maybe this doesn't make it any better, but basically we find if we were to just put our points along the number line here, okay, we've got 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, okay? And now we're to put dots for every point. So we got a dot at 12, a dot at 10, 9, 8, 2 dots at 3, and a dot at 4, okay? And we find the mean, right? We go 4, 5, 6, 7. So the mean is right here. So if the mean is right here, we take the distance here, all right? So that's the distance from the mean, and we square it. So we take the distance from the mean, we square it. We take the distance from the mean, we square it. Distance squared, distance squared, distance squared, distance squared, okay? And if we did that and we found the average, we would get something close to the standard deviation, except we're not doing the average, we're dividing by n-1 for whatever reason, okay? So it's kind of a working definition in terms of words here. And there we have it. Okay. And again, it's a measure of spread, so the standard deviation. So it's easy to get lost in what these formulas mean and all this process here. But the overall concept, the most important concept, is that the standard deviation is a measure of spread, okay? Okay. Bigger standard deviation means more spread. And smaller standard deviation means less spread, okay? Spread, again, is the idea of, are your points far away from the mean, far away from the center, or are they clumped close together in the center, okay? And if they're all far away from the center, then you'll have a big standard deviation, big spread. If they're clumped together in the center, you'll have smaller spread, smaller standard deviation. Yes?
Just a question.
Okay.
Instead of squaring it and then square rooting it,
Yeah, okay. So you're talking about this absolute value concept. We can do that, all right? And it's not the standard deviation. It's a different measure of spread, except the problem with that is it doesn't, the standard deviation puts a little bit more emphasis on outliers, okay? So if you've got large outliers, it really throws off your standard deviation, but if you just did the absolute value, it wouldn't change it too much. So don't worry about it. We're squaring it, we're adding them up, and we're taking the square root of everything. Okay, so that's yes?
Is this different from variance? And I hear those two terms thrown around.
Yes, okay. Variance is, and I'll just throw it out here, and it's not covered in the book, I don't think. Maybe it'll be covered later. But variance is everything except for taking the square root. Okay, so variance is equal to the standard deviation squared. So if you did steps 1 through 5, you end up with the variance. Okay, doing step 6, where you take the square root, that gives you the standard deviation. All right, so variance is standard deviation squared. But don't worry, we're just going to move on. All right. Concepts of standard deviation okay, or at least the steps behind it, that's okay? That's feeling all right? If it's blowing your mind, just hang in there, all right? Okay, we're going to move on to chapter 5 here, okay? So chapter 5 is called Understanding and Comparing Distributions here, okay? But really, yes, it's about understanding comparing distributions. And the big tool that we're using here is the 5-number summary and the box plot, which is highly related to the 5-number summary. Okay, so let me just get into the 5-number summary here. Okay. And the 5-number summary is called thus because it summarizes a distribution with 5 numbers here. Okay, and those 5 numbers are the minimum, the first quartile, the median, which is also the second quartile, the third quartile, and the maximum. Okay. So we've got 5 numbers: the minimum, first quartile, median, third quartile, and the maximum. Okay, and thus by having the 5-number summary, you can trivially find the IQR because you just do Q3 minus Q1, and you'll have the IQR. You'll also have the range because you just do the max minus the minimum. Okay, so you kind of have an idea of where the center is. You also see where these numbers lie. Okay, now I don't need to define any of these any more than we have already, okay? Okay. So we can compare distributions using the 5-number summary. Okay, other numbers that statistics that we use for comparing, on the other hand, so this all gets into the IQR and the range and things like that. On the other side, we have the mean and the standard deviation. Okay, and these two numbers also provide a good summary. Okay, but there's our advantages, strengths, and weaknesses for both sides. Okay, and so the 5-number summary, okay, is most useful for skewed distributions, okay? So these are most useful for the skewed distributions. Meanwhile, the mean and standard deviation are most useful for symmetric distributions. Okay? But they're both useful in any case, okay? So the mean and standard deviation is still useful in skewed distributions. The 5-number summary is still useful in symmetric distributions, but mean and standard deviation are most useful for the symmetric cases, and 5-number summary most useful for skewed distributions here, okay? And so let me just draw an example here and show you what their corresponding 5-number summaries might look like. Actually, I do not have an example of such a thing. Okay. But anyway, this is the 5-number summary. I'll just get into box plots, and box plots derive directly from 5-number summaries here. Okay. So let's see. Okay, box plots. These are graphical tools. Okay. Basically, that show the 5-number summary. Okay, sort of. All right. Okay, so a box plot, what a box plot looks like in its most simple form is you've got a box. Sometimes it's called a box and whisker thing, all right? And maybe you guys have seen these before, but it looks something like this, and then you've got, perhaps if there's an outlier, it might look like that, okay? But this is what a box plot looks like, all right? And this has no meaning because we have no numbers on it, and I didn't even tell you what this is a box plot of. But the components of a box plot is that you have this line, you have a box, okay, and there's three vertical lines in the box. All right? The middle line, this bar in the middle, that's the median. Okay? And this bar, this boundary of the box, that's the third quartile, and this boundary of the box is Q1, okay? And we might be tempted to say that this is the minimum and that's the maximum, but I have to make a caveat here and say a lot of times it is the minimum and the maximum, but a lot of times we also have outliers, and if we have an outlier, it is no longer the minimum and the maximum, okay? So I have to, this, okay? So the true meaning of this point is the smallest point within, and I'm going to get to this concept here in a moment here, but it's called within the lower fence. And then over here, we have this point is the largest point within the upper fence. All right, and I haven't talked about what these fences are, but okay, whoops, within the upper fence. But I will get to that. Okay. And the lower and the upper fences, these are imaginary boundaries that we create that distinguish regular points from outliers, okay? And I haven't talked about what outliers are either, but what they sound like is exactly what they are, okay? So the idea is you've got a whole bunch of points together, and then maybe you have one point that's really far away from everyone else, and that would be considered the outlier. Okay, so I'm trying to think if there's a good example, but well, I don't know if you guys ever remember from the 2000 Sydney Olympics. There was this swimming race, and there was this one guy from Equatorial Guinea, and it took him like 2 minutes to finish this race that normally takes the other competitors like 45 seconds or something like that. Okay, and he was like the slowest racer in in Olympic history. Okay, and probably your average Californian might be able to beat him in a pool, but they were promoting, the Olympic sports in these lesser athletic countries. Okay, and so the distribution of times. Okay, so the fastest was about close to 40-something seconds. So the distribution of times looked something like this. Okay, so we had a bunch of these are short times. Okay, and this is already at 60 seconds, and we had a couple people that were considered very slow by Olympic standards. Okay, and our friend, what was his name? Eric Musambani. Okay, Eric Musambani, he was over here at 100. I don't know, close to 120 seconds, like 118 seconds. Okay, so this guy is an outlier. All right. So the bulk of points are over here. The guy that's way over here, this is an outlier. Okay. So outlier. Okay, and outliers, a lot of times when you have data, you're tempted to throw them away. Do not throw away your outliers. Always investigate as to why you have this outlying data. It could be something as simple as a typo. When someone's typing in the information, they mess something up, they inserted an extra 0, they put the decimal in the wrong space, and that's why it's wrong. And then in that case, correct the mistake and you no longer have an outlier. Or maybe something interesting is actually happening. Okay, and in this case we had athletes from lesser athletic countries being represented. Okay, if you look up the video, it's pretty great because the whole stadium, or not the arena where the pool is located, all right, they all start just cheering, and there are all these like Australian people cheering, saying like, "Come on, mate! Come on, mate!" until he finished, and then you get this standing ovation at the end. And in an interview, he just said he's like panting and exhausted, and he's just like, "I feel good." So it's a great story. All right. Okay, so making this box plot, and I still have to talk about what the lower fence and the upper fence are. But let me see if I can find, let's see if we can find some data here. All right, so we'll go back to that one example with the heart rates and the pulses and the, where did they go? All right. So again, so if we had the heart rates, we had, what was it, 56, 60, 64, 64, 64, 68, 68, 68, 68, and then, I don't know, 72. This data is coming from page 50 again. We did this in the first lecture. Okay, and we have 24 women. So we find the central point, and so that's going to be between 12 and 13. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, and 13. So the median is 72. Okay. Quartile 1 is going to be between 1, 2, 3, 4, 5, 6, and 7. So Q1 is 68. And Q3 is going to be between 6 and 7 on this side. So 1, 2, 3, 4, 5, 6, and 7. So Q3 is equal to 80. All right, 1, 2, 3, 4, 5, 6. So here we can already form the, this is going to be tricky, but we can start making the edges of our box plots. So here I'm going to just draw a scale towards the bottom. And I'm going to put 50. We're going to space out a certain distance and go 60, 70, 80, and 90. OK, so the median we put at 72. So this is going to be the middle line in our box. Q1 is at 68, so we go down to 68, and that's going to be right there. That's the left edge of our box. And Q3 goes up to 80. And so this is the box here.
Those lines, they fall between the same numbers on each one, but if those two numbers were different, would you take the number Q1 lowest?
If these were different, you would take the average of these two numbers to get Q1. If these were different, you'd take the average of these two to get the median. If these were different, you'd take the average of those two to get Q3. Yeah. OK? All right, so here we've got the boundaries of our box here. OK? And so now let me talk about what the fences are. OK? So the fence, all right, the idea behind the fence is this is the boundary before we start getting into outliers. And what we do is we take the IQR. IQR is Q3 minus Q1. So in this case, it's going to be 80 minus 68, or basically this distance. OK? And we go out 1.5 times the IQR in this direction. So we go 1 IQR and then half of an IQR out in this direction. And so we have the upper fence somewhere around here. And we go out 1.5 IQRs in this direction. So we go 1 IQR and about half of that, so somewhere around here. And we go out in this direction, and that's our lower fence. So in formula terms, I guess, the lower fence is defined as the first quartile minus 1.5 times the IQR. Okay? And it's always going to be 1.5 times the IQR. That's the lower fence. And the upper fence is going to be the third quartile plus 1.5 times the IQR in that direction. So we go Q3 plus 1.5 times the IQR. So in this case, what is our IQR? Our IQR is equal to 80 minus 68, which is 12. OK? I'm hoping this is OK. Our first quartile is 68. OK? So we do 68 minus 1.5 times 12. So here we have 68. So our lower fence is 68 minus 1.5 times our IQR of 12. So 1.5 times 12 is 18. So 68 minus 18, that's equal to 50. OK? And over here, Q3 is 80, and we're going to add 1.5 times our IQR. So we have the upper fence is 80 plus 1.5 times 12. And we get 1.5 times 12 is 18. 18 plus 80 is 98. OK. Were any of these steps too crazy? This is OK? All right. So I'm going to indicate where the lower fence and the upper fence are with dotted lines. So I've got a lower fence at 50 and an upper fence at 98. So that's my lower fence and my upper fence. OK. So the ends of the whiskers here, this is the smallest point within the lower fence, and this is the largest point within the upper fence. OK. So in this case, the smallest point within the lower fence is 56, which is also the minimum in our data set. OK? So we have 56. That's the smallest point in our data set. OK? and it's the smallest point within the upper fence, so this is 56. This is actually not quite spaced out correctly. 56 should be closer over there. All right, and over here, the largest point that we have within the upper fence is 88. So 88 is somewhere around there. And there is our fancy schmancy box plot. Okay. Is this okay? Yeah, we have a question.
What is the point of doing an upper fence and lower fence?
Okay, so in this case, having an upper fence and lower fence didn't make a difference because we didn't have any outliers in our data set, okay? But let's say Lance Armstrong, okay, or the female equivalent of Lance Armstrong was included in our data set here, and we took this woman's pulse, and she bicycles 300 miles a day, and so she has a pulse of 36, okay? So we replace the number 56 with 36, okay? Does this change our median, Q1, or Q3? It does not, okay? So none of our numbers, Q1, median, Q3, have not changed, which means our box has not changed either, right? And the location of the upper fence and the lower fence also have not changed because those depend entirely on the quartiles and the IQR. So because our quartiles and IQR have not changed, our upper and lower fences have not changed either, okay? But it does change something over here, all right? The smallest point within the lower fence is no longer 56, but the smallest point within the lower fence is now 60, okay? So 60 becomes the end of this whisker, okay? So our box has now changed to be over here with a 60. And now I've run out of space here, so I hope it's okay that I erase all this. Is that all right? So I'm going to go ahead and erase this. And now we have to represent Miss Lance Armstrong with a 36, okay? So not Sheryl Crow, but someone who cycles just as avidly. All right, so 40, we go out to 40, and we go out to 30. And so this number 36, this is considered an outlier. And all outliers are represented with stars, okay? So we get a star at 36. Okay, so can you guys see how that has changed things, okay? And if I were to replace this 60 with someone else, let's say someone who has a pulse of 40, okay? Again, our quartiles, our location of the quartiles have not changed, okay? And so our upper fence and lower fences stay the same, okay? If we change enough numbers where our quartiles are starting to change, then we have to redo all of these calculations. But I'm purposely changing these numbers at the extreme ends so our quartiles don't change, okay? So here, now the smallest number within the fence is now 64. So that whisker goes down to 64. And then we have a star at 36 and a star at 40, okay? And this is her twin sister that has a slightly higher pulse. I don't know. Okay. But, okay. Creation of box plots, is this okay? Yeah, we have another question.
Where does the 1.5 come from? Where do you multiply it with
Why are we choosing 1.5? Okay, just take it as that's what we do, 1.5 IQR, okay? It turns out that when you apply the normal distribution and you multiply it by 1.5, you have to be outside of the range of 99.8% of the things, okay? But yes?
You can plug this into, you can plug the quartiles into the calculator and it does the box plot, right?
Sometimes yes, sometimes no. It depends what brand of calculator you have. Some brands of calculators find the quartiles in a slightly different way than we teach in this class, okay? And finding the quartiles has always been something that statisticians have argued about, and we're just going to go with the way the book teaches, okay? So if your calculator goes exactly the same way as the book, that's fine, but if it's different, just go the way of the book. Yeah. We have another question, yeah?
So there can be more than one outlier on one side?
Yeah, you can have, if you got 20 outliers, they're all going to have stars, okay? And if you look...
20 outliers if they're all in the same place, though?
Because outlier is not about... an outlier is determined by its distance from the center, okay? So you find out where the median is, okay? And you choose that as its center, and then based on the quartiles, then you've got this range of the fences, and anything outside of the fences, whether they're clumped together or not, is going to be an outlier, okay? And you have to have these really extreme cases for you to have a whole bunch of outliers clumped together. But things like if we were to look at the income level of people in California, you know, most people would be clumped in this middle class range, but then you've got a bunch of CEOs from Silicon Valley that will all be outliers, and they'll all be in this million-plus range, but they're all outliers still, okay? All right, so anyway, so now that we have this box plot tool, we can look at different distributions. We can look at the box plots of different distributions. Which is essentially, basically, if you're given a box plot, you should be able to create the 5-number summary from the box plot, correct? Okay. And if you're given the 5-number summary, you might be able to create the box plot, okay? If there's no outliers, you can definitely create the box plot. But if there are outliers, then you might have trouble creating the box plot, because then you don't know where the smallest point within the lower fence is and stuff like that. But given a box plot, you can recreate the 5-number summary. Okay. Standard deviation. Where did it go? Okay, so this is an example from the book. All right. Oh, so far I've done my box plots horizontally, but sometimes you'll see the box plots drawn vertically. Okay, and it's no different. It's just now they've done them vertically and they put it on there. But we'll do an example just so when you do your homework you don't freak out. Okay, so we got 40. Okay, and so this is roller coaster speeds, all right? So we measure the max speed of all these different roller coasters, okay? And we classify roller coasters as either steel roller coasters, or wooden roller coasters, all right? That's the, I went on a wooden roller coaster recently. That was pretty good. I was impressed. I think it was at Knott's Berry Farm. Ghost Rider or something. That was a good one, all right? So we got this slow steel roller coaster. So the slow steel roller coaster is like 40 miles per hour. That's like Gold Rusher or something. You ride that when you're in 3rd grade because you're too short to ride the big rides or something. Okay, and it looks like the median is about 65, and we go up to 100, and then we get an outlier at 120. Okay. All right. Meanwhile, wooden roller coasters are at 60, and I don't know, something about there. Okay, and so this one is steel, and this is wooden. All right. Okay, so what can we say about steel roller coasters and wooden roller coasters. I hope you guys at this side of the classroom can see okay. Okay, yeah, in general, steel roller coasters go faster, okay? We still have some roller coasters. You can find a steel roller coaster that's just as slow as a wooden roller coaster, okay? These steel roller coasters are, just as slow as whatnot, okay? But you look right here, okay? So what is this? This line is this is the median, okay? So that means, and this corresponds to right about here, and this is what? This is Q3 of the wooden roller coasters, right? So your average, the median speed of steel roller coasters, okay, is faster than or just as fast as 75% of wooden roller coasters, all right? So one thing we can point out is the median of steel roller coasters is just as fast as, the 75th percentile of wooden roller coasters. Okay. And, the fastest wooden roller coaster is maybe just a hair over the 75th percentile of the steel roller coasters, okay? So you have no, so definitely the top 25% of steel roller coasters, because this is the 75th percentile, this means the top 25% of steel is definitely faster than any wooden roller coaster, okay? So wooden roller coaster, okay? And and we in fact have a steel roller coaster, an Outlier, that goes 120 miles per hour, okay? And so this might be interesting to investigate. How does a roller coaster even go that fast? 120 miles per hour, okay? Terminal velocity for a human going out of an airplane at, free falling is like 120 miles per hour, okay? So this is a roller coaster that's going just as fast, okay? And actually, it turns out that this has some sort of launching system that rockets you out of the gate at 120 miles per hour, rather than not using just gravity to get you going so fast. But okay, so anyway, looking at two box plots, you should be able to make some general statements about comparing these roller coaster speeds or numbers in general. Okay. Other questions on any of this stuff? Okay. The rest of Chapter 5, when you go into the book, it talks about re-expressing data. We're just going to skip that section. It might be worth skimming over, okay? But don't stress too much about that. We can still have a very worthwhile and meaningful statistics course without covering these topics, okay? I hope no one's too disappointed, and looking forward to the re-expression of data. Okay, how are we doing on time? Okay, 8:05. That's pretty good. Okay, and so I'll get into Chapter 6 here, and the rest of this class time we'll devote to Chapter 6, because this is a beefy chapter. And then we'll take a break somewhere in the middle here, okay? All right, hang in there. All right. All right, the chapter title is Standard Deviation as a Ruler and the Normal Model, okay? But it's mostly about the normal model. But the standard deviation is important, okay? All right, so okay, so the example that the book uses, it's pretty good, all right? And it's about the women's heptathlon in Olympics, okay? There's there's 7 events, all right? And 2 of the events are the long jump and the shot put, okay? And the highest performing long jump was this woman Carolina Kluft, okay? And the highest performing shot put person was, I don't know, Miss Ostra Scuite. I can't even pronounce her name. But let me just put the we're going to put the mean and the standard deviation, and we'll talk about the long jump and whatnot. So we've got the mean and the standard deviation, okay, and the number of contestants. And this is, we'll put Miss Kluft and Miss Scuite something. All right, she's from Lithuania. Anybody know how to pronounce this? Scuite. All right, so the mean long jump was 6.16 meters, all right? The standard deviation of the long jump was 0.23 meters, and there were 26 contestants there. So this is long jump. Okay, and this is shot put over here. And for shot put, the mean distance that they threw the shot put was 13.29 meters. The standard deviation was 1.24 meters. And there were 28 contestants over here. All right, so Kluft, she was the highest performing long jumper, and she jumped 6.78 meters, all right? And Scuite jumped 6.30 meters. Kluft on the other, Scuite on the other hand was the highest performing shot putter, and she threw her shot put at 16.40 meters, and Kluft threw her shot put at 14.77 meters, okay? So here we are trying to compare, figuratively speaking, apples to oranges, right? We know Kluft did better than Scuite here, and we know Scuite did better than Kluft over here, okay? But who was the, quote, more remarkable performer between Kluft and Scuite if we're looking at these 2 events, okay? And how can we look at this, right? We've got the mean at 13.29. They both performed above average with the shot put, and they both performed above average on the long jump, okay? Except she did a little bit better than here, and she did a little bit better than this person over here. So how can we compare this? If we were to draw the distributions, okay, for the long jump, the histogram looks kind of like, I don't know how to do this. All right, this is just a rough sketch. Okay. Oh, I'm sorry. This is, I have my sketch backwards here, okay? So better is this way, okay? Better performance is in this direction, okay? And so this was the long jump, and this is cleft here, okay? That's cleft. All right, and then for the shot put, again, better performance is to the left, so my thing is backwards. Generally, higher numbers you go to the right, but here I put them backwards. Better performance goes this way. And the shot put looks something like this. And this outlier here, maybe not an outlier, but this person by herself is Skewed. All right, so we want to be able to make a comparison between cleft and Skewed, and we can see that they kind of set themselves apart in both the long jump and the shot put. Okay. All right. So to make a comparison, I'm going to introduce this concept called the z-score. All right. Z-score. The z-score. So over here we're dealing in meters, okay, and over here we're also dealing in meters. But the average is 6.16, and over here the average is 13.29, and over here the standard deviation is 0.23, and the standard deviation is 1.24. Okay. So the z-score kind of, I'm going to say, normalizes these things. Okay. Maybe I shouldn't use that word normalize, but it kind of puts everything into the same scale or into the same terms, okay? So the z-score is the number of standard deviations above or below the mean a certain point is, okay? So every point that we plot, every point will have a z-score, okay? If those points are very close to the mean, they will have very small z-scores. Their z-scores will be like 0 or 0.1 or whatever, okay? If those points are far away from the mean, then they will have high z-scores, z-scores of like 3 or something, okay? It's, in general, you don't see z-scores much bigger than 4 or 5, okay? Generally, the biggest z-scores you'll generally see are about, 3 something, okay? And those are pretty extraordinary. And of course, these are rules of thumb that depend on the numbers you're looking at, okay? All right, so the z-score is the number of standard deviations above or below the mean that a certain point is, okay? And we can put these into standard deviations because, again, standard deviation is the idea of the average, the square root of the average squared distance from the mean, okay? And so that's like the typical distance that a point might be from the mean. And so by comparing them in terms of standard deviations, we can see which point is more extraordinary or not. Okay? So the formula for a z-score is given by y minus y bar divided by s. Okay? Let me also write, sometimes you will see y minus mu divided by sigma, okay? These are parallel in concept here, okay? And again, y bar represents the sample mean, mu represents the population mean, okay? And s represents the standard deviation of the sample. Sigma is the standard deviation of the population. Okay, I don't mean to try to confuse you with all of these duplicate versions, okay? But one is for samples, one's for populations. Just remember that for means, okay, we have y bar is the sample mean, and mu is the population mean, all right? Okay, and then for standard deviations, S is the sample standard deviation, and sigma is for the population. Okay, so you'll see either one of these things. Okay, what you won't see is y bar mixed in. Well, actually, that's not true. Sometimes they'll mix them up. Okay, but in general, you'll either see one of these. Okay, and the idea is, if I want to just write them in terms of words, you've got the point of interest minus the mean divided by the standard deviation. Okay, it's the same for both forms here. All right, so let's find the z-score, Kluft's z-score and Skewed's z-score here, okay? Okay, so here, let's see. All right, so let's find, let's calculate the z-score for Kluft's long jump here, and we'll calculate Skewed's z-score for her shot put throw. Okay, so Kluft's z-score is given by z is equal to the point of interest that we're interested in is 6.78. So I'm going to just write Kluft's z-score, long jump z-score. Is this all right? So 6.78, that's the point of interest, that's our y, minus the mean. The mean is 6.16 divided by the standard deviation of 0.23. Okay. All right. Is where I'm getting each of these numbers. Okay, we have a question.
What if your point of interest is smaller than your mean?
That's also fine. You will end up with a negative z-score, okay? Because a z-score is the number of standard deviations above or below the mean. So if you have a point of interest that's below the mean, you'll get a z-score, but it will just be negative, and that tells you that your point of interest was below the mean. Okay? In both of these cases, these were the top performers, so both of them will have positive z-scores that were above the mean, okay? Because they both performed above average. Okay, so everyone's okay with where I got the 6.78, the 6.16, and the 0.23? The 6.16 is the mean of the long jump scores, okay? So here we've got Kluft's score, the point we're interested in is 6.78. That's our y. The 6.16 is our mean, okay? That's our y bar. And the s, that's the standard deviation of that, okay? And the n doesn't play a role in our z-score here, okay? So here we do 6.78 minus 6.16. And now I need my calculator. And we divide this by 0.23. So 6.78 minus 6.16 divided by 0.23. And I get 2.70, okay, or 2.695. I'm just going to round off to 2.70. So Kluft's long jump was 2.70 standard deviations above the mean. So above that average point, her long jump score was 2.7 standard deviations above the long jump. Okay. One thing to note is that z-scores do not have any units. Okay, so no units on z-scores. They're just the number of standard deviations, okay? All right, so let's find Squeete's shot put score. Is this getting too cluttered? Maybe I'll just, I'm going to just erase over here. So Squeete's z-score, Squeete's shot put z-score, that's going to be z is equal to, her shot put score was 14.77 minus, oh, I'm sorry, 16.40. I'm sorry. Thank you. Thank you for pointing that out. 16.40. Her shot put score was 16.40, and her mean, the mean, not her mean, but the mean of all shot put scores was 13.29. And we divide by the standard deviation of 1.24. Okay. And again, is everyone comfortable with where I got all three of these numbers? Okay. And so when we change this into a z-score, we get 16.40 minus 13.29 divided by 1.24. 2.51 I get. 2.51 standard deviations above the mean. Okay, so even though we're comparing two different things, Clough's long jump score is more standard deviations above the mean than Squeete's shot put score. You guys see that? So Clough had a long jump that was 2.7 standard deviations above the mean. Squeete had a shot put score that was 2.51 standard deviations above the mean. So if we were to just try to make a comparison between these two, we would say Clough's long jump score is more impressive than Squeete's shot put score. Okay, both of these are very impressive. Again, rarely do things fall outside of 2 standard deviations, okay, much less 2.7 or 2.5 standard deviations, okay? But and if we had to choose one, we would say her long jump score was more impressive than her shot put score, okay? We're just we're comparing standard deviations. So you can't just say, you know, 0.78 is what, 0.6 something higher than 0.6 meters higher, and this one is, I don't know, 3 something meters bigger, and so 3 meters is bigger than 0.6 meters, and therefore it's different, okay? You have to look at the standard deviations here. Yes?
If this was being counted in time opposed to meters, then it would have been the second one that was better.
Yeah, of course you have to look at the context of the problem here, okay? And so if smaller scores were better, then yes, the other one would be better. But in our case, bigger is better, or higher numbers are better, and so that's why we're saying this one is bigger. Okay. All right, is that okay? Okay. And before we get into the normal distribution, and I know you guys are so excited to learn about the normal distribution, I have to talk about shifting and rescaling data, okay? So in Chapter 5, we skipped a section called re-expressing data, but in Chapter 6, we have to cover something called rescaling data. There's no way around it, okay? And it's not a hard concept, okay? I might be saying that about too many things. Well, let's see what time it is first. Oh, you know what? Let's take a break. And I've got 8:26, so come back by 8:40. How's that? 8:40, I'm going to get started back up.